Hello student, welcome to our third lesson. We are still looking at stability of isotopes of elements, but in here we are going to discuss radioactive decay and half-life. Now, when a radioactive nuclide decays, we have seen that a new nuclide with different composition is formed. As disintegration proceeds, fewer and fewer unstable atoms remains. Now, the table below shows the radioactive decay of a sample of 400 grams of iodine 31. That is what we have here. We have the time in days and mass in grams of radioactive iodine that is remaining. We start with when the time is 0 days. It had a mass of 400 grams. Then after 8.1 days, the mass that is remaining was 200 grams. When it went to 16.2, we had 100 grams. Then 24.3, we had 50 grams. 32.4, we had 25 grams. And the process continued until at 48.6, we had 6.7 grams, 75 grams that was remaining. So in other words, we have seen that as the disintegration or as splitting occurs, we will have fewer and fewer unstable atoms that are remaining. That is what is happening on this side. This is the mass that is remaining. Then we can plot a graph of mass of iodine remaining, that is on y-axis, against time in x-axis. And when we plot, we have this kind of a graph. We have the mass that is remaining on the x-axis, on the y-axis, and the time in days in the x-axis. As you plot, you know, I'm sure you know how to plot, but we can just see that at 0 days, this is 0. Then the mass is at 400. That is what we have our point here. At 8.1, the mass is at 200. At 16.2, the mass is at 100. At 24.3, the mass is at 50. At 32.4, the mass is at 25. At 40.5, the mass is at 13.5. And finally, at 48.6, you will find that the mass is at 6.25. You can as well plot when you have your graph paper and see whether you will get this kind of a curve. Now, when you look at this curve, there is one thing I want you to note, that if you want to move from 400 to 200, that is half of 400, that is 200, you will need 8.1 days. Right? Now again, from 200, the half of 200 is 100. From this point up to 16.2, you will get again is 8.1 days. Then the half of 100, that is from 16.2 to 24.3, again you will find that it is 8.1 days. That is the difference between that 24.3 minus 16.2, you will get 8.1 days. Again, this is 50. So a half of 50 will be 25. So to go to 25, it will be again after 8.1 days. So in other words, we are getting half of the present mass after 8.1 days. So it implies that after 8.1 days, half of what is there will have decayed. And it implies that the remaining will be half. So in other words, 8.1 days is the time taken for half of this or the present gram to decay by, or the half to decay. So we can see the explanation that we have here. From the graph, it can be seen that after every 8.1 days, the amount of substance remaining is half the previous amount. That one we have seen. The fractions of the original remaining after 8.1 days is a half. Then the second one will be a quarter. The third one will be an eighth. In other words, after 8.1 days, we are getting half of what was the previous amount. It is also observed that the remaining amount never reduces to 0. Although it is approaching 0, if you look at our final value there at 48.6, it is 6.75. it is approaching 0, but it never reduces to 0. The time taken for the mass to reduce to half the previous value is constant. And in our case here, it is 8.1 days. We have seen that. We started from 400 grams, we went to 200 grams, and that took 8.1 days. From 200 to 100, again it took 8.1 days, and the process continued. Now this time is denoted by T1/2, and we call it half-life. So we can define half-life as the time taken for the half of the number of nuclei initially present in the radioactive sample to decay. Note that we are talking of the mass that is initially present, the half of the mass that was initially present to decay by half. That is what we call the half-life. From the sample of 400 grams of iodine-121, the amount remaining will be, we started with 400 grams. The first half-life is 8.1 days, so we went to 200 grams. Then the second half-life will be 8.1 days, you get 100 grams. You go to the third half-life, which is 8.1 days, again you go to 50. So you can continue until you get the number of half-lives that are intended, and you will be able to get the mass that is remaining. So the amount remaining after the first half-life is half the previous amount. So it implies that after the first half-life, the mass that is remaining is half the previous amount. In other words, we are saying 200 is half of 400 grams. Then 100 grams is half of 200 grams. Then 50 grams is half of 100 grams, and the process continues. So the remaining amount after successive nuclide decay can be worked out. We can use the following formula. We have a half, then to power n times the original amount, where n is the number of half-lives, or the amount of half-lives undergone. And we can look at an example here. What is the remaining amount after 24.3 days? Remember, we are using our example. So 24.3 days is 3 half-lives. So we can proceed as follows. A half to power n, our n is 3, then times 400. So a half to power 3 will be 1/8. Multiplied by 400, you get that it is 50 grams. Then, given the remaining amount, the original amount can also be determined. For example, if 3 grams of this element whose half-life is this, that is 8 seconds, remaining after undergoing radioactive decay for that is 2 seconds, what was the original amount? You are given the half-life, and you have been given the time that is 32 seconds, and you're given 3 grams that are remaining. So we proceed as follows. The number of half-lives, remember it has taken 32 seconds, and we are given that the half-life is 8. So for us to get the number of half-lives, you get the total number, or the total time taken divided by the half-life. So you get 32 divided by 8, you get 4 half-lives. So we have a half, we are using our formula, to power n, that is the number of half-lives, which is 4, multiplied by the original amount is supposed to give us 3. So we are supposed to get this original amount. So our original amount will be 3 divided by this 1 to power 4 is 1 to power 16. And when you are dividing the fraction, you always multiply by the reciprocal. So our original amount will be 3 times 16, which is 48 grams. From there, we can have another method that we call linear method. We can use step by step as follows. You had 3 grams, and we are moving 4 half-lives. So it means that at 4th half-life, you are supposed to add this one, that is, you get 6. Then the third, you move times 2, you get 12. The second, you move times 2, you get 24. The first, you get times 2, you get 48. So it implies that if the remaining was 3 grams, and it has gone for 4 half-lives, then the original value was 48 grams. This is what we call the linear method or step-by-step method. Then from there, we have that each radioactive isotope decays at its own rate, and therefore it has its own half-life. You can't say that because you have this one is close to this, it has the same half-life. No, each radioactive isotope has its own half-life. We have examples here. We have the nuclide, as you can see here, and the half-life on this other side. All these are isotopes, and they have different, as you can see, it is ranging from seconds to years. For instance, you have carbon-14 here that is taking 5,000 years and more. And then you have this one that is just taking 8 seconds. So in other words, we have those elements that have a longer half-life and others that have very small or few seconds as their half-life. Then from there, the shorter the half-life, the faster the rate of decay of nuclide. And the longer the half-life, the slower the rate of decay of the nuclide. So the rate of radioactive decay is not affected by any chemical or physical change. Remember, when we are looking at nuclear reaction and chemical reaction, we say that in nuclear reaction they are not affected by physical change, whether temperature increases or pressure, they are not affected. So we are saying that the rate of radioactive decay is not affected by any chemical or physical change. Now, the half-life of a radioisotope is one of the factors that determine the application. For instance, we have carbon-14. We have seen that carbon-14 has a half-life of over 5,000 years. And this carbon-14 is used to determine the age of dead organic matter. And that process, we call it carbon dating. Now, what happens is that when the carbon in a plant or during the process of photosynthesis, the plants take carbon. And as they take carbon that is necessary in the process of photosynthesis, they take a portion of radioactive carbon-14. Now, when the plants die, this carbon-14 in the dead plant continues to decay. Remember, it is unstable. It is radioactive. So it will continue to decay, and therefore its amount decreases. So carbon-14 has a half-life of 5,600 years, and therefore by determining the carbon content in the dead material, the age of that sample can be determined. For example, we also have sodium-20 with a half-life of 0.3 seconds. Look at this now. We are comparing carbon-14, which is taking years, 5,000 years, and sodium-20, which is just taking 0.3 seconds. Now, due to this smaller half-life, it is used to detect leakages because it has a short half-life. So we are saying that the half-life determines the application of isotopes. We have seen carbon-14 for carbon dating, sodium-20 to detect leakages. Then from there we have the assignment. This assignment again is testing what we have just learned. We have seen a graph like this one. So therefore, if you find that they are difficult, it's always good to revisit your video, listen again, and then come and attempt the assignment. So thank you, and let us meet in our next lesson.